Welcome back. So, we're going to kind of take the next evolution or the next step into the GPS side of things, and we're going to look at the accuracy of a GPS and the errors that we encounter with them. So, to kind of begin with, we kind of clearly established that, for a GPS receiver to work, we need to have a nice, good, clear view of the sky. And, a couple things to think about and kind of question yourself on this is imagine what happens if I'm in a big city, as you can kind of see by the representative photo there. So I'm standing there on the ground, and my GPS satellite receiver is picking up the same signal from the same satellite, except all four signals that, as we see there, are coming in at different time codes because they're kind of getting bounced around off of the buildings. So now the question becomes to the GPS receiver, which one is the trusted one? So one of those maybe is correct. How do I know? There's some other things that we think about is maybe we've heard this from time to time where we hear about solar flares and its impact on radio waves, picking up radio signals. Well, the signal coming from our satellite is a radio wave. It's a radio signal in essence. So what happens with solar flares? So what we do see happening is that we have errors coming in our signal. So we're picking them up, and so we try and the GPS receiver has to try and diffuse those and figure out which one is correct, or what is my exact location. And a lot of this, what's going to do, it's going to determine what we call our GPS accuracy. And that's a term you're going to see. If you look at a GPS receiver, any of the basic ones like that you pick up to go hunting or fishing with, or what's in your vehicle, or what we see on the agricultural equipment, they have an accuracy value. And it's going to say GPS accuracy. So if you're questioning yourself, what is GPS accuracy? Here's what it is. Basically, the GPS accuracy is a measurement of how close a GPS receiver can get us back to the exact location where that location was stored. So if I'm out about with my GPS receiver, and I get to my ideal fishing spot, and I say, this is an awesome spot, I want to store this location so I come back to it. So I go to my GPS, I say store this location, it's going to store it as a latitude and a longitude, and then I walk away. Well, let's say at some future point I want to go back to that fishing location, so I pull up my receiver, I say, yep, take me to this location. The accuracy is going to be how close did it get me back to that exact location that we logged before. And so it could be maybe it gets me within 2 feet, 3 feet, 10 feet, 20 feet, whatever it may be. So GPS accuracy, when you see that value, is how close can it get you back to that original location. So what are some things that kind of throw that accuracy or kind of bring the accuracy into play? Well, one of the biggest ones we see is what we call atmospheric effects. So as we found out in the earlier video series, GPS receivers are sitting up there at about 11,000 nautical miles, 12,660 miles. Since up there quite a ways, there's a couple different layers of the atmosphere, and those atmospheres have different masses. So as that signal's coming down, as it hits that different mass, that signal can be deflected. It's the same thing if you think about when we go to shoot a bullet into the water. The bullet, as soon as it hits the water, since that's a different mass, is going to alter its path. It's not going to go straight in as we were aiming. Same thing happens here. So as that radio signal hits the different layers of the ionosphere, the troposphere, that signal is going to get deflected or move away a little bit. So nice thing is we can kind of account for that. Another example where we see error, kind of explode this area, is what we call the multipath error, where my signal is going to get bounced off, or it's going to get reflected off of other objects first before it is picked up by my receiver. So the issue at hand here becomes okay, which signals are the correct signals? So some other potential errors that we see is satellite orbit. So the satellites orbiting above, there's some natural phenomenon. Since they're orbiting up so high, there is some gravitational forces at play from the sun and the moon. So it has a tendency to try and pull those satellites a little bit out of their orbit. Some other things we see, as I mentioned earlier, solar radiation, solar flares. When the sun kicks off some abnormally high solar flares, that impacts that radio wave. and once again could lead to some potential errors what's coming into our satellite receiver. So a lot of these natural phenomenals, they're going to create very small errors, and those errors will start accumulating over time. The nice thing here is, since our satellite system is being monitored by the Defense Department, a lot of times they're constantly monitoring that and they are adjusting it. So they go in those clocks and say, yep, it's off by a little bit, so adjust the clock by this amount. So another potential error that we see for GPS receivers is just the receiver themselves. And it goes back to, there is price does matter. You can see some really cheap GPS chipsets. They're really cheap. Well, the cheaper they are, the not as accurate as they're going to be. Because what we do see is some of them actually have better clock units inside. So they have a little bit better timing chip built into them. Sometimes it's that electronic internal noise. Anything electronic is going to give off frequencies and gives off waves, electronic noise. Some of them don't, are a little more particular to that. Some factor that out. And another one is that we do see some that have basically a higher mathematical precision. So they, do the calculation out into a lot more decimal points than what some other ones are. So that actually has an effect on what our GPS location is. Now, an issue that we did have, there was what was called selective availability, or SA for short. And what this was a Department of Defense program. So what the Defense Department did is they actually degraded the GPS signal. So they intentionally degraded the signal down. And what that would do is basically it distorted it. So our receiver, instead of trying to get a more precise location, says, well, that signal's somewhat distorted. I'm somewhere within a 100-meter range, or 300 feet. So think about it. The signal is being distorted by 300 feet. So you could be standing at one end of the end zone of a football field, and basically from there take a radius going all the way to the other end of the end zone at the other end, and making a big giant radius all the way around that. Your GPS receiver would say, well, I know I'm here, but I could be somewhere inside this 300-foot radius going all the way around me. So the question is, why would the Department of Defense do this? The reason they did this was they were afraid that maybe there's going to be some other entities out there, some people who are not very friendly towards the U.S., who would actually use our GPS system against ourselves and attack us. So they deliberately distorted it just to prevent people from using their own system against them. So when the system first came out in '93, we had the SA signal in there, went to Congress, it was being discussed, and officially President Clinton signed it into law in late part of 1999, early 2000. President Clinton signed it into law and had it discontinued. And so officially it was turned off on May 1st, 2000. And when they turned that signal off, then the accuracies got a lot better because the signal wasn't being distorted as much. Something to note is the September 11th, 2001 attacks. There was some talk there soon thereafter of, well, did the terrorists use GPS against us? Maybe we need to turn selective availability back on. There was just a little bit of discussion, but then the long-held belief was it was going to happen regardless if the GPS helped them or not. So the selective availability signal has stayed off, was never turned back on after 9/11. So to kind of show you, someone was actually recording their GPS receiver location. They had a very precise location, said, yep, this is where my GPS receiver is at. And they were recording their position at the time that selective availability was turned off. And so you can kind of see here on May 2nd, 2000, kind of leading up to it, starting at midnight, you can kind of see there on the left-hand side of that chart is where it thought its location was. And we're basically anywhere within we even had some that were getting out close to 120 meters, 360 feet out. A bulk of it was in that 50 meters or less. And then once the signal was turned off, at 6 o'clock that morning on May 2nd is when the system was actually turned off, you could see all of a sudden the accuracy now went down into about 10 meters or 30 feet. And that is something that has been fairly common that we've known. You're going to kind of see where this 10 meters comes into play later. So with that turned off, now our accuracy is down to about 10 meters or 30 feet, just raw GPS signal itself. So our GPS errors, as we kind of look at it, where do those errors come from? Well, we've looked at the atmospheric effects of getting that signal bounced through the different layers of the atmosphere. There's the issue of multipath, where we could be bouncing off of objects first before it gets to us. The satellites orbiting themselves. The quality of the GPS receiver. There's also just a little bit of that satellite clock drift comes in. Once again, same thing with satellite orbit. It's being monitored by the DoD. And then, of course, we had selective availability. That was part of the initial error. Well, that's been turned off, so we don't have to worry about that anymore. But you take these errors and you add them up, and what we get is our GPS errors are actually going to determine what is our GPS accuracy. So, we have a budget when it comes to GPS, and this is how we're budgeting our error. So we know the ionosphere up there, the larger part of the atmosphere, that could distort our signal by distort the signal by upwards of 5 meters. The troposphere, the one a little bit closer, well, it can distort the signal maybe up to a half a meter at the most. FMS data, that is just basically data, that's that satellite clock, that satellite drift, what we've seen in there. Along with the satellite clock drift, 1.5 meters, 2.5 meters for the FMS data. Multipath, if I'm standing out in the middle of a field in Iowa, I'm not going to see that because it's not bouncing off anything. But once again, if I'm in a larger city like some of the major cities, we could see potential error there of a half a meter, 0.6 meters. Noise of the equipment. This is electronic noise, the measurement noise, 0.3 of a meter. And like we said, we had selective availability that was 100 meters. Well, we don't have to factor that in. If you take those first 6 errors up there from the ionosphere all the way down to measurement noise, if you add those up, that gets us to those 10 meters that I talked about earlier, which is roughly about 30 feet. So a GPS receiver without any assistance, the best it's probably going to get us is to about within 30 feet of its original location. Here's an example. There's actually there's free software out there that you can get where you can plug in a GPS, and it's going to sit there and it's going to monitor its GPS location, and constantly it's taking its position every couple seconds and it's plotting it. So this is plotting software, and you can see this was over a 2-hour period, and you can see kind of the differences that we were seeing with that GPS. So, 95% of the time it was within about 5 meters of itself. And then 95% of the time it was within a 15 meter radius. So that's just kind of the GPS accuracy. Now, something that can also affect our GPS accuracy, it's what's called delusion of precision, or DOP for short. So what delusion of precision is basically it's a measure of the geometric quality of the satellite configurations up in the sky. So when it's looking at the satellites that are up in the sky. What is their positioning in relative to each other? And so that's giving us our geometric quality, and that actually has an effect on our location of our GPS location. So what it does, it measures it and it comes back with a numeric value. And we can see it expressed in 3 different ways. One of those is what's called the horizontal delusion of precision, or HDOP. We also have VDOP, which is the vertical delusion. So horizontal would be basically on the Earth's horizon. Vertical would be going from the horizon up into the sky. And then the third one is kind of a combination of HDOP and VDOP. It's what we call PDOP, which is our position, or our 3D position in terms of delusion. So next slide will kind of explain this here. So take a look at that image up in the upper right hand side. You can see what's called a high PDOP, and you can see where the satellites are really close together. So as that signal's coming down, as it's kind of getting spread out, it's going to give us a larger area of uncertainty. Versus if I look at that other image where it's the low PDOP, where the satellites are spaced spaced widely apart or far apart, it actually narrows down my uncertainty area. So HDOP is kind of on the horizon, VDOP is that vertical kind of going up in the sky, and then PDOP is kind of a combination of the two. Well, in precision ag, HDOP means a lot to us, as does the PDOP. Vertical VDOP doesn't mean a lot to us because we're not doing a lot of things in terms of vertical. Those in the airline industry, those are flying, VDOT becomes something for them because it's more of up and down, not just on the horizon. So what it is when we do that measurement, what we're looking for, the lower the number, the better it is. So if we have a DOP value of less than 1, that is considered ideal. That is the best. And then from a 1 to 2, it's really good. It's excellent. 2 to 5 is good. Once we start getting above 5, then we're going to start calling in the question of how accurate is our GPS. That quality is really going to start falling off. You can see where 5 to 10 is moderate, 10 to 20 is fair, and if it's over 20, it's really poor. And if it's over 20, it's probably not. Your position is going to be way off to where it doesn't even. It's not going to work. It's not going to pay off. Why even have the GPS at that point? So this came off of my precision ag system last year. Just you can do this. A lot of modern displays will actually are recording those values and doing that calculation. So you can see there's my HDOP, my VDOP, and my PDOP outlined there in red. As you can see, it's fairly low. And like I said, the nice part is if you're out in rural areas, it's a pretty broad area. The chances that you're going to get satellites that are nicely spaced out because you could see them in a broad open area becomes a lot better. So DOP is one of those things that affects the accuracy of our GPS and something we need to think about. And you could see this, we've seen this in time and time again, where growers or people are like, hey, my GPS, it's not acting right, what's going on? A lot of times the technician's going to have you go in there and check these DOP values and look and see if there's something going on with the satellite orientations of the satellites up in the sky. So anyway, that concludes this part of the lesson. So coming up next, we're going to talk about how we can take these errors and try and get a better fix or a better position through the use of correction signals. So till then, thank you.